Okay, so let's go ahead and review kind of what we talked about today. So to start class, we went over the 1.3 practice a little bit. So this is something you may want to go back and look at. In your email, you should have gotten a released score email, and you can view, you can open that email and hit view, and it will display your homework questions again to you. And then you can make corrections on your paper for things you might have missed. So one thing we talked about was interpreting standard deviation. And this sentence on the screen right now is like I wasn't actually presenting anything. Here we go. Okay, so this sentence is how you want to interpret standard deviation. So it's how much it varies from the mean, the data. So how like spread out it is. So on this question in particular about the hamburgers, you can kind of see in the dot plot, it's like, yeah, it's kind of crazy, but like they do give us the standard deviation, which is kind of a big number. Like basically what it's telling us is like if you have a hamburger, on average, it's about 9 grams of fat away from the average. So in this case, it would vary a little bit. Now, if it wasn't that far away, so let's say the standard deviation was like 2 grams of fat, then we would say, well, it's not very, then it wouldn't vary too much. Like so the standard deviation is that distance from the mean. So to interpret it, we just want to kind of use the sentence as the safest one to use to make sure you don't interpret anything incorrectly and get docked for it on the AP exam. So this says insert the context. So in our case, we would say the amount of grams of fat in a hamburger typically varies by, put the number 9.06 from the mean of 22.83. And that's it. So that's interpreting standard deviation. So it's your on average, how far are your data points from the average. So the bigger the standard deviation number, usually the more spread out your data. The smaller it is, the more compact your data. Okay. So the other one we looked at was to decide if something was skewed. So a lot of people noticed, hey, if there's outliers, like definitely something is probably skewed. The other quick way to tell is if you're given a printout of data, so kind of summary statistics here. We've got basically the mean and the median we can compare, because the mean gets pulled in the direction of the outliers. It just kind of gets yanked over. So if the mean is kind of greater than the median, meaning it's heading towards the right of the median, we'd have a right skew. And similarly, if it's to the left side, we'd have a left skew. So that's another quick way to tell is which way is your mean being pulled, because it's a calculation. So if we're adding in extreme values that are too big or too small, it's going to pull that mean on one side of the other of kind of where your typical center is or your median. So the other thing we looked at is the 1.5 rule, which determines outliers. So some people looked at one of the homework questions and said like, oh yeah, that's a pretty big number. I think it's an outlier. It might be an outlier, but you do need to calculate it. So you do need to actually compute this value to make sure you understand you have an outlier. So you do have to do this math. And so as long as you have your summary statistics here, you can find the IQR, which is the difference between your quartiles, and then multiply it by 1.5, subtract, add, and then you're good to go. If anything falls outside of this number you get or this one, then it's an outlier. So always make sure you're doing that part. So then what we looked at today is who's the best home run person, who's the greatest of all time in terms of baseball. So we looked at Barry Bonds because he broke Mike McGwire's record of 73 home runs in a season in 2001. So we want to start investigating like, all right, well, who's better? So we looked at this data. This is Barry Bonds, his distribution of number of home runs in these seasons, across these seasons. And we noticed like, 73 is kind of disconnected. That's crazy. It's a little bit varied. It's kind of roughly symmetric because we do have like some extreme values in there. Now, then what we did is broke into groups and drew all the graphs. So I'm going to kind of show you some of the graphs that we got. So one group did box plots, and this was kind of our box plot. Now, if you notice, There's no disconnected values in our box plot, no little starred points, so technically there's no outliers. We would also want to test that with the 1.5 rule, which I'll show you, and it will reveal that technically there are no outliers in Barry Bonds' data set. So the 73 that he got was legit, wasn't really an outlier. Another group, we already kind of looked at the dot plot, just, number line, put your dots. The stem plot, we generated pretty quickly too. So that also kind of reveals that gap here, but again, it's fitting in our 1.5 rule if we calculate. And then a histogram, you've got here as well. So that kind of also reveals that gap and shows us where kind of our values fall. You can adjust the width of your bars. So like if I change this to 20, it's going to adjust the shape a little bit. So basically I'm looking at how many values fall between 0 and 20, and I count those up. So there were 3 of them. How many fall between 20 and 40? Count those up, so on and so forth. But again, the grouping class did use widths of 10 and counted up how many values fell within those widths. So we then kind of looked at the key and we summarized some advantages and disadvantages, which you can kind of look over, just kind of reminding yourself what each graph shows you. So kind of summarizing the differences and similarities here. The other thing we then did is describe the distribution. So we want to make sure you have context, shape, center, outliers, and spread. Now here's the work for the 1.5 rule, which will reveal there is no outlier. 73 is just fitting into our data and is not an outlier, so that's great. So since we don't have outliers, we could, in theory, do use standard deviation for spread if we wanted to, because there's no outlier, so we know standard deviation is not impacted by any crazy values, so it's probably pretty accurate to describe the spread that way. The other option is to use your IQR, or your difference between your quartiles, to describe spread. Either is fine. Shape, a little debatable if you had the box plot question. If you look at a box plot, shape sometimes can be a little hard to determine. But here what we could look at is the lines in the middle. These bars are kind of the same length, the whiskers of our box plot, sometimes these are called. So those are kind of similar. So we could get away with saying this is roughly symmetric. Even, this isn't an outlier. If you said slight right skew, it would probably also be counted. So if you had a box plot question and had to describe shape, they're always a little more flexible because it is a little harder to see. So the other thing then is our center. So we could use the mean if we want, since there's no outliers. You could also use the median here. So whichever one you pick is fine, since there's no outliers in this data set, to throw off your mean or your standard deviation. But when in doubt, median and quartiles, difference between your quartiles and your quartile range is also always safe, no matter what. Because those are not calculated from the data, those values, the median and the IQR, those are locations in the data set. So they're not impacted by any crazy crap, basically, any outliers. So then what we looked at is Mark McGuire's stuff, his data, which it does, again, look roughly symmetric. And we do have a value of 70 here. And we have some of the summary stats. So if I was going to compare the two players, we would want to look again for context, so the number of home runs. And we're comparing them. So you could get away with saying Barry Bonds and Mark McGwire, they're fairly symmetric. Both are fairly symmetric. Then for the center, if you want to use the mean, you can. If you want to compare the medians, you could. But for this case, the mean is slightly higher for Mark McGwire. The medians are actually the same. So you could say those are similar to if you use the median. Just make sure you're saying which value you're using, so we can understand, which way you're trying to compare things, and if that comparison is correct. And then if you want to use standard deviation, again, you can, which is given here. And if you happen to have it for the other set, you could use that again. So just kind of showing you an example where you could do that. Or if you want to use your IQR, your difference between these two, you can compare those numbers to Barry Bonds, and then just say which one is greater or which one is less. So the comparative language piece is important. So when you're describing a measurement, you do have to say how it compares to the other values. So is the center of Barry Bonds greater or is it less than Mark McGuire? And you need to use the words greater than or less than when comparing those values. You can't use the word while because that is not a comparison word. That is just the word while. Like it doesn't say greater or less. So that's what you kind of have to look for. So that's an example here of that, what would get kind of full credit. One thing on the AP exam is you don't actually have to put the exact values. You don't have to put the numbers as long as you're saying the mean or the median when you're describing center. Tell us which one you used. You don't actually have to put the number. So that is chapter 1 review. So tomorrow we have more review things to make sure you're prepped for Friday's test. So if you do have questions, please make sure you come to tutoring from 1 to 2 via the class meet, or schedule an appointment with me via the Google site. The homepage there has that make an appointment button. If you can't find any of that, shoot me an email and I can help you out finding the things.